Okay, great. Okay, well then let's get started here. XL13, June 25th. We are already halfway through 2015, over halfway through the 2010s decade, and hurling through space and time. All right, so, but you have all decided to spend 12 weeks of your life learning statistics. Okay. Anyone here taken statistics already? You have. So why are you taking it again, if I may ask?
It's required in that, pre-med list or whatever. So
And your other statistics class didn't count, or oh, you need 2 stats classes?
Yeah, I believe so. So I took XL10 last quarter.
What? Who'd you take 10 with? Baltar? Rojas? Siavash.
Yeah.
Siavash Halal. Yeah. Interesting. You need 2.
It's just on the list. I think I have to go through every course that's listed to, complete my pre-med requirements.
Okay. Well, double check on that, because you might not need to take this class if you did 10. And what about yourself?
I'm just filling the requirements for the certificate.
Oh, and you have to take the.
One class is fine.
Okay. All right. Well, okay. How did you enjoy the XL10?
Yeah, it's okay.
Okay.
It's not like super hard.
All right. Well, yeah. I don't know. Okay. Well, we'll see. Okay. So statistics. So I love statistics, and I got my, I started my undergraduate degree in engineering, and then I took a statistics class, and it changed my life. I finished my engineering degree, but then I decided to go back to grad school to study statistics, and I got my PhD in statistics, and I'm, now I'm teaching it, and I'm hoping to communicate to you how awesome statistics is, and how, you can see the world through it. So statistics, let's see. So let me just start off with this. Okay, we study statistics so we can have Okay, so I start off with this lofty sentence, right? We study statistics so we can have a better understanding of the world around us. And I would argue that this probably can be said about most subjects that you would study. You study chemistry to have a better understanding of the world around you, and that you can study, how molecules and things react, and you study history to understand the world around you, and that you study the past, and you study all of these different disciplines probably to have a better understanding of the world or humanity or whatever it might be. What statistics allows us to do, okay, statistics allows us to make meaningful conclusions based on limited data. All right? And so I'm going to just draw one little diagram here. And this is, in my opinion, kind of a nutshell of what statistics is all about. Okay? So meaningful conclusions based on limited data. All right. So let's say you have a research question, okay? So let's say you have some research question, such as, is medication XYZ an effective treatment for disease ABC. Okay, so let's say you want to know, is some proposed medication an effective treatment for disease ABC? Okay, and so we have something called a population. The population is everyone relevant to your research question, okay? Okay, so in this case, who would be the relevant population that we would need? Yeah.
Anybody who has disease ABC.
Yeah, every single person, any person who has disease ABC would be our population. That would be everyone relevant to the research question. So in this case, everyone who has disease ABC. Okay? Now, there's no national database of people who have disease ABC. You know, as much as the government and NSA or whatever might want to know everything about our lives, they don't, okay? And probably nobody should know every single thing about our lives. And so there's no way we can track down every single person in this population, because the only way we would know who has disease ABC is be to test every single person in the world with some magical test that says you have disease ABC or not. Then we can say, okay, now we've identified everybody with this disease. And then to answer the question, is this an effective treatment, we would then have to administer this treatment to these people and see how they react to the thing, okay? So everyone who has disease ABC, the idea being this population is too big for us to study directly. Okay? So instead of studying the population, we study a sample. A sample instead of the population. Okay, and the sample would then be a selection from the population that we hope is representative of the population. Okay, so the sample is a selection we hope is okay. Is everybody able to read my handwriting okay? Okay, that's good. So the sample is a selection from the population that we hope is representative, and based on what we see in the sample, we infer conclusions about the population. Okay, so this diagram is this thing is our population. It is too big, and so from the population we take a small little piece, and this is our sample. Okay? And based on what we see, so this is yeah, we select a sample, okay, and based on what we see in the population, we then make inferences about the population, okay? So instead of trying to track down every single person who has disease ABC, maybe we get 150 volunteers who have disease ABC, okay? And then we're going to have to do some kind of experiment or something, okay, to see if the medication is an effective treatment. And if it's an effective treatment for the people in our sample, we are then going to try to infer and say, well, ideally, we would infer and say, because it was effective in our sample, we're going to then conclude that it is effective in the population. Even though we didn't see every single person in the population, if it's effective in our sample, we're going to conclude that it's effective in the population. Okay. And it doesn't have to be medication. It could be just anything. It could just be, you know, what is the average weight of a Labrador Retriever, a grown Labrador Retriever? I don't know when they reach maturity, 3 years old or something like that. So what is the average weight of, you know, and so if everybody relevant in that population would be all Labrador Retrievers, and then to answer the average weight, you would need to then track down every single dog and weigh them, and then calculate the average. Of course, that's not practical. So maybe you can take a sample and maybe observe 100 dogs, and then make a conclusion about the general population. Yes?
So is there like a minimum for a sample? Like, is there like a certain percentage that like, it has to be? Because obviously you wouldn't take like 2 dogs, you know?
Well, you could take 2 dogs, and your conclusion about the population would be, you can still make conclusions about the population, but your conclusions will not be very specific, okay? So, right, if you took a sample of only 2 dogs, your conclusion would probably be, I'm pretty sure that the average weight, you know, let's say the one dog was 45 pounds and the other dog was 60 pounds, okay? You would then say, you know, I'm pretty confident that the average weight of all dogs, all Labrador Retrievers in the world is going to be between 10 pounds and 90 pounds or something like that. That would probably be a realistic conclusion based on your sample of 2 dogs, something like that. But, you know, that's not a very useful statement. So, you know, if you want your statement to be useful, you're going to need to take a larger sample, and maybe after looking at 50 dogs, you can get it within plus or minus 5 pounds, and maybe take a sample of 1,000 dogs, maybe you can get it plus or minus 3 pounds or 2 pounds or something like that. But anyway, yeah, so we'll talk about the specifics of that kind of stuff later on. But just here, the big picture is, here's a population, or we can think of a population. It's too big for us to observe directly, so we're not going to try to do that. We're going to just take a small piece of that. We observe the sample, and based on what we see in the sample, we're going to then infer things back about the population. Okay? And so this works by, in statistics, a large part of statistics is understanding variation, okay? So in statistics, we try to understand variation, okay? And so what I mean by variation is that in life, we learn very quickly that everything is different and everybody is different, right? Everything and everyone is different, okay? Even identical twins, they are different. Even if they share the same genetic code, they are different people with their own thoughts and things, and there might be things that are very similar, but they're still different, okay? And you know, if you look around, well, even in our classroom of 7 people, you guys are all different from each other, okay? But then you're also similar to each other in certain ways as well, right? Everyone here has, you know, eyes and hair and nose and mouth and things like that, okay? We easily identify each other as human beings because we share certain things in common that make us human, but we also recognize that we're different, right? Similar and different. And so variation, when we talk about understanding variation, there's the idea of there is natural variation from one person to another, and we kind of have an idea of how much things are supposed to vary from person to person. And if something was drastically different from that, that would stand out to us as unusual, okay? So for example, just regarding human height, if we saw someone who is 7 feet tall, something in our brains would say, wow, that person is very, very tall, okay? Because in our human experience, we're used to seeing, you know, most people in the range of 5 feet to 6 foot something-ish, you know, maybe some people a little bit shorter than that, some people a little bit taller than that, but we don't very often see people who are 7 feet tall. And so if that happens, our brain says, wow, that's unusual. And so we already have an inherent understanding of variation, especially for things that we are familiar with, okay? So, so how can I summarize this? Okay, so our brains already have an inherent understanding of variation to a degree. Okay? We are not surprised to encounter a person who is 6 feet tall. Okay? However, we probably would be surprised, be a bit surprised, to see someone 7 feet tall. Okay? I don't know if surprised is the right word with the right nuance, but just there, our brains would flag that as, oh, that person's tall. That's a little bit different. And statistics allows us to understand variation for things that where we haven't, you know, had, you know, X amount of years of life experience, right? So throughout your whole life, you've been encountering people, and so your brain has built up this range of stuff. But then you encounter something new, and you're not. If in a new subject, you don't know, oh, is this a big value or is this small? Okay, and statistics allows us to just kind of look at some numbers and then right away say, oh, this is unusual, or this is within the range of usual, okay? So, for example, anytime maybe you have a friend who's really into sports, or you're really into sports, okay? And they might say, oh, so-and-so accomplished this, right? They threw the ball this many feet, and you don't know if you should be impressed by that or not. But they might say, well, you know, so far everybody, you know, most people are only within this range, but this person was, you know, way out here. So that's impressive, okay? And so statistics kind of will give you the idea of what's what's within the range of ordinary versus extraordinary. Yes?
I noticed reading newspapers and books, even watching TV, a lot of it is statistics.
Mm-hmm. Yeah. So it's, like I said, I thought this subject was great because it can be applied to many aspects of life, and putting kind of certain things into a context. Okay. So statistics allows us. So I'm using statistics as like the subject. Allows us to understand what kind of variation is usual versus unusual. Okay. And we, okay, so here's an example of usual versus unusual variation and how statistics might help us out. Okay, and so I'm just going to do one example from Chapter 1. So Chapter 1, Section 1 just kind of gives a bunch of different examples of things we might encounter in our class. Okay, and so we're going to start off with, this is an experiment done with lab rats or lab mice. And
Should
yes.
we be doing our books class, or
Should you be what?
bring our books class, or is that unnecessary?
I don't know. That's I can't tell you. I mean, if it's difficult for you, I think it's good to have your book, but you know, if it's annoying to carry your book, you don't have to bring it. Okay, so we took some mice and we exposed them. Well, we divided them into two groups. Okay, one group of mice we put in an E. coli environment. We exposed them to the bacteria E. coli, and then the other group of mice we kept in a germ-free environment. Okay, and we had a total of 62 mice, and for whatever reason we put 13 in the E. coli environment and 49 in the germ-free environment. Okay, and after they had to live in these environments, we dissected all the mice, and we saw that some developed liver tumors and some did not develop tumors. Okay, so two groups of mice. Okay, and at the end some developed tumors and others did not. Okay, and we want to know, and I'll put the numbers in here, but the question we're asking is exposure to E. coli linked to an increased risk of developing tumors? Okay, this is the question that we're going after. Okay. Okay, and so we looked at our mice, and those in the 13 mice in the E. coli environment, 8 of them developed liver tumors, 5 did not. In the germ-free environment, 19 developed tumors and 30 did not. Okay, and so what do you think? Can we answer this question? Is exposure to E. coli linked to an increased risk of developing tumors? Well, how would we go about answering this?
Isn't it out of the total? So it's like you just kind of figure out the percent, like.
Okay, so what would we say? So we could say, all right, so for E. coli, 8 out of 13 developed tumors. If I punch that into the calculator, I do 8 divided by 13, and I get, about 61.5%. Okay, and for germ-free mice, so the mice in the germ-free environment, 19 out of 49 developed tumors. And that corresponds to 38.8. Okay, so let's say we've done this. We've done these calculations. So what do you think? Is exposure to E. coli linked to an increased risk of developing tumors?
Yes.
Yes? Who thinks yes? Richard thinks yes. Anybody else? Anybody else willing to say anything?
I think they need to do more.
You need to do more, maybe? Okay.
It's a higher risk in E. coli, but it doesn't seem conclusive to me that it's definitely linked.
Okay, so what do you mean by it doesn't seem conclusive?
Well, 38.8% is actually still a decent amount. It's not 2%.
Okay. All right, so yeah, so this brings up a good point, right? Someone could argue that at the beginning, 27 mice were destined to develop tumors and 35 were not, okay? We could just say if we had 62 mice, somebody could say, let's say 27 mice were destined to develop liver tumors no matter what. Whether we put them in a red box or blue box or an E. coli box or germ-free box, these 27 mice were going to develop liver tumors anyway, okay? And we could have had 2 germ-free environments or 2 environments that were identical, put 13 mice in one box and 49 in the other box, and just from the random mixing up of the mice, 8 of those 27 mice could have ended up in box 1, and 19 of the liver tumor mice could have ended up in box 2. Could that have happened just by random chance? It could, okay? It could have happened. And so if that had happened, okay, then we know that in that case, which box they got assigned to has no influence on whether they developed liver tumors, okay? If we just had 2 random boxes, one was labeled box 1 and the other was labeled box 2, and I decided to throw 13 mice over here and 49 mice over here, it could be that out of these 27 liver tumor destined mice, 8 of them end up over here, 19 end up over here, okay? That is technically possible, and if that did happen, then we know it's not that the boxes are causing liver tumors, it's just that was a result of random assignment, okay? On the other hand, let's say our data ended up, having all 27 over here and 0 over here, okay? Or something like, we had a very drastic thing. Now, technically, if our data ended up much more extreme, technically it's still possible. And it's still possible that just from random assignment alone, we observe this unusual result. But we're going to study probability, and we would see that it's technically possible, but it's highly improbable. And because it's highly improbable, we would then conclude that it probably didn't happen by random chance, but rather it happened because something else is going on, not just we threw the rats in different boxes and they ended up this way. Okay, and so what we're going towards through this class is we're going to try to distinguish between, okay, 61 versus 38, or 62 versus 39%. Could this result have happened just from random assignment and random chance, or is this actually evidence that the E. coli and the germ-free, or that the different treatments actually make a difference? That's what we're headed towards. Okay, and we're not going to answer this question today, but maybe week 7 we'll get there. Okay, week 8. So there's a question. So let me just kind of sum all of this up. Okay, so naively, we may say 61.5% is greater than 38.8%. So E. coli is linked to linked to higher risk of tumors. However, it is also possible that the results we saw in our table came from random assignment. Okay. So we want to distinguish between the possibility of getting our results through random chance versus an actual effect. Okay, and so Chapter 1, Section 1 just gives you more examples of kind of where we're headed, and this is just a small little example that we will see in Chapter 9 in our class, or Chapter 10. Okay. Does this make sense, these statements here? Okay, so let me just kind of give a mini map of the course. So we're going to start off with descriptive statistic. So today we're going to talk about descriptive statistics, just how to describe data, what kind of variables we have. So this is descriptive statistics, which is all about describing data. So this is what we will do today, okay? And then next week we're going to cover basic probability, and probability distributions. Okay, so we've got rules of probability, and we will also have, maybe I'll start off with probability like this. Okay, and then we will have probability distributions. Okay, so we've got rules of probability, and then we apply them to what we call random variables and probability distributions. Okay, so examples of probability distributions would be things like the normal distribution and binomial. And from there, we're going to learn sampling distributions. Okay, and so sampling distributions, we'll explain exactly what that is, but it's a kind of an application of probability distributions. Okay. And then once we learn sampling distributions, we're going to then bring back the descriptive statistics and what we've learned from sampling distributions. We put them together and we will get into statistical inference. Okay. And when we do statistical inference, we're going to just cover a whole bunch of different types of tests depending on the situation that we find ourselves in, okay? And so this is kind of the first half of the course. Up until the midterm, it'll be up just to get to our first encounter of statistical inference, and our first encounter of this will be creating confidence intervals. Which I'll explain when we get there. And this will take us up to the midterm. Okay. So this will be our midterm exam. Okay, and then so after our midterm, then we get into a bunch of different statistical inference methods, okay? Okay, and these all depend on the different situations that we find ourselves in. And so, we're going to, learn how to deal with situations with numeric response variables and versus categorical response, and then we've got all sorts of different situations depending on so a bunch of different statistical inference methods, okay, and which one we use depends on the situation we face. And so, so that will be after the midterm. Okay, so prior to the midterm, it's going to be kind of laying all of this foundational stuff, and sometimes it feels a little bit unrelated until we tie it all together. But this is where we are. So today will be this, and then week 2, week 3, and week 4, and then week 5. So I don't know if I should label these. So this will be week 1, 2, 3, 4, 5. That takes us right to the midterm, and then all of the statistical methods we'll cover in 7, 8, 9, 10, and 11. Okay. All right. Let's see here. Okay. So let's get into maybe just a little bit more foundational work right before we get into the descriptive statistics, okay? So just I want to talk about observational studies versus experiments. Okay, so these are both methods to gather data. Technically, there is another form of evidence that we don't really consider to be statistical evidence, and that would be like anecdotes. Okay, so we have anecdotal evidence. Both methods to gather data, and I'll just write as opposed to anecdotes. So anecdotal evidence would be instances such as, my aunt had this disease and she drank some herbal juice and it fixed her problems and now she's healthy. Okay, and that is that's a true story. That we're not doubting that happened. But it doesn't necessarily mean that the reason why she got healthy was because she drank the herbal juice. It could be. The herbal juice could be the reason why she got healthy, but it's not necessarily also the reason why she got healthy, okay? There are many different things that could go in and affect someone's health, and herbal juice might be one of those things. It might not be, okay? And so just because it happened to one person, or even if it happened to 5 different people that you know, that is not proof that this would happen to everyone in the world either, okay? And so anecdotes, if it's not in the setting of, kind of a controlled study or an actual study, it's hard to know if there's any merit to the claims produced by the anecdotes, okay? Observational studies versus and experiments, on the other hand, are legitimate ways to gather data that we can analyze statistically, okay? And so with an observational study, we generally do our best not to interfere with our subjects other than taking measurements and doing the observing, okay? We generally try not interfere with our subjects other than observing and taking measurements. Okay. And, we do realize that just the very act of observing may influence our subjects, but there's not much you can really do about that, okay? Yes?
So I'm taking a psych class right
Uh-huh.
now, and they talked about how that's considered like research? Is observational study and descriptive research like the same thing?
Ooh,
Instead, it's just like watching kids on a yard play, like you're observing them.
Descriptive research versus quantitative research, you mean? Is that what you're going for? So observational studies can be descriptive research. They can also be quantitative research, okay? So
it could be measurements.
yeah, you could be taking measurements and you could do statistical analysis, okay? So observational studies could go either way. It's what I'm talking about here is how we are gathering the data, okay? You know, you could do experiments, but the measurements or the records that you take are descriptive also. So that, okay. So we generally try not to interfere with our subjects other than observing and taking measurements, okay? So we do not assign treatments. To the subjects. Basically, subjects self-select, okay? Okay. If we want to know, we might do an observational study on the effects of exercise on health. And we would not say, you have to start exercising. We're just going to observe. Some people will choose to exercise, some people will not. We are not telling them who needs to exercise and who doesn't. That's an observational study. As soon as we tell somebody, you've got to exercise, then it no longer is an observational study. Okay? And so the key thing about an observational study is that we can find associations between variables or factors, but we cannot establish cause and effect. Okay, and so here's you know, perhaps you do a study and you find that vitamin D deficiency is linked to some condition, you know, some symptoms. Okay, now in this observational study, we didn't tell people you need to do things so you get more vitamin D. We didn't say you have to go into the sun or you aren't allowed to go into the sun to get vitamin D or drink milk or whatever. You know, maybe we just are observing vitamin D deficiency is linked to, you know, low bone density or something like that, okay? From a study like that, we cannot then say the reason why people have this condition is because of the vitamin D deficiency. All we can say is there seems to be a link because it was an observational study, okay? And I know sometimes we want to jump to these conclusions and say, oh, you know, this study revealed that people low in vitamin D had, you know, these types of problems. Therefore, you know, you should take vitamin D supplements to help avoid these problems. That is not what you should conclude from an observational study. And a silly counterexample would be, you know, we could look at different households across the United States, and we can look at the number of appliances in the house. Okay, so appliances being, you know, televisions, dishwashers, blenders, things like that, just household appliances. And what we would find is that homes with lots of appliances, more appliances, will tend to have children that perform better in school. And homes with fewer appliances have children that tend to perform more poorly in school, okay? And so, I mean, this is a silly example, and nobody would then say, oh, well, the solution to education would then be to supply more appliances to homes and that's going to make our problems go. We know that would be a silly thing to conclude. But you know, if you mix up appliances with vitamin D and this condition versus education or whatever, then suddenly it feels like, oh, this is what we should do. And so in that case, we know it's not that the appliances are causing bad test scores or anything like that. It's just there's kind of this catch-all term, socioeconomic status and income and things like that, and somehow it's accepted as fact that households with lower income generally have children who perform more poorly in school than households with higher income. But that in of itself doesn't explain why either. We can't just say the solution to education is just give people more money either, because that doesn't explain everything either. So there's something else going on, much more complicated than just money or appliances or things like that, linked to test performance and things like that. But I think we would agree that it would be silly to say that the appliances are causing problems in education, and it would also be silly to make the same kind of conclusion to say vitamin D deficiency is causing this problem, okay? Until you do an experiment that establishes a cause and effect conclusion, you cannot make cause and effect conclusions from observational studies, okay?
Well, you're saying that you said there were two situations, observational studies and experiments.
Yes.
So we're learning about observational studies and what you can't do in it. You must experiment instead.
Yeah, so an observational study is, so basically, a lot of times we do observational studies because experiments are not ethically or practically possible, okay? And that's fine. We can still make good conclusions and make good associations at the results section of our observational study, but we cannot make cause and effect conclusions from an observational study.
Being a human being, we can't do certain things to human beings, so otherwise you have to do the opposite.
Right. If we wanted to know the effects of cocaine on a adolescent mind, we cannot ask for volunteers and then say, okay, thank you for volunteering, you're now going to start using cocaine and we're going to see what it does to your brain. Okay, that would not be an ethical experiment, so we can't do that. The best we can do would then be to do kind of observational studies and quote unquote hope, or if there ever is an encounter where an adolescent has used cocaine, we can then study that person's brain and then try to draw conclusions from it. But because we are not assigning the treatment, the user self-selected, it complicates things, because there could be many other factors going into why this person chose to use cocaine that could have also influenced the brain. It could be something was wrong with the brain and that's why the user chose to use cocaine. We don't know, okay? So anyway, okay, so anyway, that's that. I don't know, so I'll just do examples. Appliances versus test scores. Okay. Or yeah, so that's one. Okay. Experiments. On the other hand, with an experiment, ideally, we can control as many aspects of variation as possible. Okay. In the, quote, dream experiment, we would have two groups. A control and a treatment group. Okay, and then both groups would be nearly identical. Nearly identical with identical environmental conditions. Okay, the only difference would be that one group is gets the control, and the other group gets the treatment. Okay, so this is our dream experiment. We have a control group and a treatment group. And everything about these two groups are identical, okay? Or as much identical as possible. They have the identical environmental conditions, you know, they have the same, they're subject to the same conditions, okay? And the only difference between this group and that group is that this one gets control and this one gets treatment, okay? And then at the end of our study, if we see there's a difference between this group and this group, that difference can be attributed to the fact that this got control and this got the treatment, and no other reason, because everything else about them was identical. So if everything else was identical except for that one thing, then any difference we observe at the end of the experiment can be attributed to that one difference. Okay, and that would be the dream experiment. On a practical level, you can't have everything perfectly identical, and so you're going to have to live with some differences, and you're going to have to kind of take that into account into your analysis. But that would be our ideal scenario. Okay, so at the end of the experiment, any differences observed between groups can be attributed to the control treatment conditions. Okay, does that make sense to everyone? Okay, so with experiments we can establish cause and effect. Okay. But then again, experiments are not always practically or ethically possible. Okay. And that's why we often have to do observational studies, just because, you know, we respect people, and we can't always get, you know, do an experiment, right? Okay, is that all right? Let me just add a few more things regarding experiments. Okay, so one aspect to make sure that both groups are nearly identical is we don't want the groups to know whether they are in the control group or the treatment group, okay? Because just the fact that they know which treatment group they're in, whether they're in the control or treatment, automatically puts a difference between the two groups, okay? And again, we don't want them to know. Okay, so in experiments, we do not want subjects to know which group they are in. Okay, and so this hiding of the group identity is called blinding. Okay. If you're using medication, you can't give one group medication and the other group nothing, because then they would know which group they're in, so you give the other group a placebo. Okay, so with medication, you use a placebo as a method to blind the subjects. Okay. If there's an evaluation to be done, so certain things, it's easy to record the effect, right? If we want to know, does a medication lower blood pressure? It's easy. You just hook them up to a machine. The machine reports blood pressure. Okay. But other things, if we want to maybe if we want to know, does something reduce anxiety? Okay. You might need a psychological professional to make an evaluation as to whether or not anxiety has improved. Okay, we need somebody to make that evaluation. There's no machine that you can just stick your hand in and says this is how much anxiety you have. Okay, so somebody has to make that evaluation. You don't want that person to know which treatment group they're in. We don't want them to know if they got the actual drug or the placebo. So that would be a double-blind experiment. Okay, so if evaluations are to be made, we do not want evaluator to know the treatment group. Okay, and so this would be double blind. Both subject and evaluator do not know. Okay, let's take a short break here.